2 times 3 to the n minus 1, plus 3 to the n minus 1, minus 1 over 2, right? What do we got? Well, what we have is 3 to the n minus 1 power over 2 of these minus 1 of these is going to be 3 to the n minus 1 over 2 times 2. You see what I'm saying? So what is this ratio going to be? This ratio basically looks like it's going to be approaching what? 1. Because 3 to the n minus 1 is a very large number. So is this. Minus 1, very small number. So pretty much this is going to, as n gets bigger, this is just getting closer and closer to 1, and therefore the ratio gets closer and closer to 2. So it's a constant. It's a constant.
How did you get the denominator again? There's 2 times 3 to the n plus 1.
3 to the power of n.
Hold on a second. So we have this, right?
Can you go
Okay,
back?
hold on a second. So it's going to be this. You got this part, right? It's over 2, right?
Is 3 to the power of n, or n minus 1. It's past.
Where's 3 to the power of n? I'm sorry.
That is 2
Then
multiplied
2x
3.
plus x is 3x.
You saying here?
Yeah.
Yeah.
No. Because this is, think of this as a value, right?
Yeah.
Think of this, so you have 2 of them plus 1 of
That's
them.
why it's 3.
Oh, 3 of them.
Okay.
Yes. Oh, okay. Thank you so much. Okay. For some reason I thought it was, yeah, for some reason I was doing a minus. So yeah. So it's going to be, okay. So it's going to be 3, right? 3 times 3 to the minus 1 over 2. Thank you. So now, that's good. So this is going to be dividing, so we're flipping it up. So it's going to be 2 times 3 to the n minus 1 over 3 to the n minus 1. So this is going to equal to 2 times 3 to the n minus 1 over 3 to the n minus 1. But again, as n goes to infinity, you're going to have 3 to the n minus 1 over 3 is going to be 1/3. So it's 2/3. So what 2/3 of the job is being done where?
67%.
Right, but where's 2/3 of the job being done? At the bottom level. So it's actually even stronger. Okay, so yeah, sorry about that. Okay, so we have 2/3. Approximately equal to 2/3. So the last level is carrying 67% of the work. So of course, what happens? What do you think is going to happen with? So it's going to be 2/3. What do you think is going to happen with power with k is equal to 4? Probably 75%, right? 75%. Okay. So you can see why a master theorem is a valid, very strong way to do it. It has its limitations. The limitation for master theorem is that it has to have the a times t of n over b plus f of n. A can be anything 1 or higher, and b can be anything 2 or higher. Or I think 1 or higher. I think this one has to be at least, I mean, it's never a problem. But basically, so this is the number, so this is the number of what? This is the number of branches, and this is the number of ways you're cutting the input in half to the next level. Okay. All right, any questions about that? I'll come back to that. Because it's interesting to how we can apply. The master theorem always gives us a what kind of result? What's the asymptotic notation we use for that? Always gives us a theta. But sometimes we can use master theorem to not get a theta. And that becomes more interesting when we have a harder problem. We can say, okay, I don't know what theta is, but here's a big O using master theorem, guaranteed. So it's also very useful. Okay. What I wanted to look at right now is I want to look at the next set of notes. Specifically, I'm going to go to lecture 4 from the text. And that has to do with quicksort algorithm. How many people are familiar with quicksort? How many people have heard of it at least? Okay, that's good. That's a good start. Okay. Nobody wants to admit they're too familiar with it. All right, that's fine. Not a problem. All right, so let's see how we can. Oh, no, it's working. Funny thing, works only, well, it's just some kind of mathematical joke, but nobody's in a good mood for jokes. So, all right, so we're going to look at quicksort. So quicksort was proposed by very famous English mathematician and computer scientist C.A.R. Hoare in 1962, and it became really a revolutionary sorting algorithm because it has a very good performance. Not all the time, but it has a very good performance. And the advantage of quicksort over another sort like merge sort is that merge sort requires, if you remember, once you have two arrays that are sorted, now you have to merge them. Well, what do you merge them into? Now you have to allocate another size of the same as these guys, and then start putting them back in here. So if you're sorting something that takes 10 megabytes, you're going to need 20 megabytes of space. So we call this overhead. So we need that extra merging area in order to finish merge sort. Okay, but quicksort allows you to sort in place, which means you don't need any more storage than what's already in the array. So it's called in place. In place. Where does it say in place? I thought it said oh yeah, okay, in place, in place. Like insertion sort, but not like merge sort. Okay. So insertion sort has that in place. It's very practical with tuning. All right, so the idea is what we're going to do is we have an array of unordered numbers. They're completely unordered. We want to sort them. Okay, and here's what we're going to do. The idea is for quicksort is that we're going to partition the array. How are we going to do that? Well, here's the idea. Very, very simple. You have an array of random numbers, totally unordered. You're going to pick a random element of those numbers, and since they're random and unordered, we'll pick the first one. And what we're going to do is we're going to place this element properly in the array. So for example, if it's the 7th smallest, it'll be 7 here and 6 below it. If it's the 15th smallest, it's going to be here, and 14 are going to be below it. Now, so we'll place it exactly where it's supposed to go. Now the numbers less than it are going to be less than it, but they will not be put into any order at all. So we don't know what these numbers are going to look like in terms of their sequence, but we know they will all be less than or equal to this element. And we don't know what these numbers here to the right of it will be equal to, but we know they're all going to be bigger than my element. The element we choose, we name it the pivot. So we take the first element, it becomes the pivot. And now we're trying to sort of be like Moses and partition the sea for this element so the element can go into correct space, and then lesser elements here, greater elements there. So that's the idea. We're going to try to find the space for it, and here's how the algorithm works. So notice that X is the pivot. It didn't start over here, but now it's pivoted here, and so all the elements to the left of it are less than or equal to it, and all the elements to the right are greater than or equal to, although I think equal is no good. We need to have greater than. It's a mistake, so it should be greater than. Okay, so now we're recursively, so once we can place this pivot into the correct location, all we need to do is then do the same thing with the left side and do the same thing with the right side. Now, the key is we really have no idea where that pivot element is going to go to. The element is coming in an unordered from an unordered array from some initial location. So therefore, it may fall here, it may fall here, it may fall here, it may fall right there where it started. It could go at the end, it could go anywhere. The probability that it goes anywhere in the array is equally likely. So therefore, the probability is going to be equally likely here, 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 here. It's a good one. Here, 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 here. So the probability is extremely high that it's not going to go in the middle. But the probability is also extremely low, it's not going to go in the end. Why? Well, because here, if there's a million elements, it's only 1 out of a million chance that it's going to be on the end. Well, there's another bad end here. It's 2 out of a million. Still, 1 out of 500,000 is not too bad. But the probability it's going to go right in the middle is only 1 out of a million. And we're banking on that. We actually think that it's good if it goes in the middle. Because if it goes in the middle, then the next level of the recursion will get n over 2 and n over 2. We're banking on a 1 in a million shot. So usually it doesn't pay off. Usually it doesn't pay off. So this is the algorithm. And an algorithm is a little tricky looking, so it's always better to look at the algorithm after you've seen what it's doing, and then go back to the code to see how the code's doing it. And so, let's take a look over here how we're going to do it. So, we have two indexes, I and j. And what we're going to do is we're going to compare. So this is the pivot element. We're going to just choose it because these elements are random right now. So what we're going to do is we're going to move this j as long as the pivot element is less than equal to that index. So j moves ahead because j is going to mark the elements that are bigger than this, and I will mark the edge of the elements that are less than or equal to. So 10 goes to 13. 13 is also bigger than the pivot, so guess what j is going to do? J is going to go forward. But 5 is not. 5 is not. So basically I is the edge of the less than or equal to. So therefore anything greater than I is going to be greater than. 10 is, 13 is, 5 isn't. So what's going to happen right now is this element has to be moved into the I location. So what are we going to do? So we're going to think about what can be done. What can we do here? Clearly, somebody said I++, yes. Clearly I has to move by one spot because I has to have two elements because 5 is less than or equal to 6, so it must come into the I partition. So watch what happens. What do we do? We bounced I by 1 to the right. We knew by going to the right we have a violation of I, because that means that this value we know is greater than pivot. But we had a violation here. This number was less than or equal to the pivot. So therefore these two elements could now be freely exchanged. So I goes up here, and the 5 and the 10 swap. So notice that now we have I marks the edge of elements less than or equal to 6. Okay, so now, guess what happens? We repeat the process. What do we do with j? Because 10 is greater than, so therefore that j partition can go. How about now? Increase again. How about now? Now we have the same deal as before. We have a violation here. This is a less than or equal to violation. So what we're going to do is we're going to create another violation here because we need to absorb that guy right here. And that guy, the 13, can just as easily go here. So therefore we're going to move I to the third location and swap the 13 with the 3. So I will now be on the edge of 6, 5, 3, and j will have be pointing to the 13. So we'll have I here, and then we'll have 10, 8, 13. That's what we're going to have. Got it? Now what do we do? J goes forward again into a violation. What's going to happen? I goes to the 10 spot, causing a violation of less than or equal to, and we swap the 2 and the 10. So now we have 6, 5, 3, 2. And now what happens? J goes to 11. And now what happens? J goes off to the right. Well, guess what? We have now, I is now marking the partition where is the edge of the elements that are less than or equal to 6. All the elements to the right of it are greater than 6. So what we're going to do is we're going to swap the pivot, which is index 1 or 0, or however you want to think of it, with index I. And so 2 and the 6 are interchanged. Once that happens, notice that to the left of 6 are only numbers that are less than or equal to 6, and the numbers to the right are greater than. Okay. So, how much work did we do? How much work did we do? To do that, we need to really look at the work that we did. So basically, the reason we were able to move j, because it was a comparison. Comparison, comparison. Okay, then we did a swap. Then we did a comparison. Then we did a swap. Comparison, 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 swap, comparison, comparison. Okay, so relative to the size of the array equal to n, how much work did we do? And so theta n work. So n, so now what is this algorithm that we just looked at called? This is called the partitioning algorithm. And the code is given right here. So you can kind of see what's going to happen here. So the pivot is randomly selected as A0, but it could be any element. But we're using A0. Okay, that's the pivot. The pivot goes into I, so I is the value of the pivot location. Okay, and then J goes to the pivot plus 1 and tries to move forward. If AJ, where J is less than or equal to X, then I is increased, and we exchange AI with AJ. And we continue. That's the whole algorithm we saw. And finally, after we're out of this loop, we exchange a P, which is the pivot, with an AI, and that places the pivot right in the spot we're supposed to go into. Okay, so you can see how that works. So this is pseudocode for quicksort. So basically it looks like this. So quicksort of the array A from P to R, where P and R are the indexes. If P is less than R, what does that mean, if P is less than R? How many elements do I have? If P is less than R, how many elements do I have? At least? At least 2. At least 2, right? Because if P was equal to R, that's 1, so I have at least 2. So I have at least 2 elements. So if I have at least, because if I don't have at least 2 elements, then guess what? It's done. If you want me to quicksort 1 element, I'm done. You quicksort this number 3. I'm done. Quicksort is 3 and 2. Oh, okay. I have some work to do. So, if there are at least 2 elements, then we call partition. That's exactly what we just did. And we know that has a work of theta n. And partition will return Q. What is Q? Q is the index where the pivot is. So Q is exactly where the pivot went to. So we know everything to the left. The pivot is correct. Leave it alone. Quicksort left of the pivot and right of the pivot. So here's the pivot. Go left of the pivot with quicksort, and then go right of the pivot. That's it. You know, recursive algorithm is like magic. Like, really, that's it. Because you see a lot more complicated before. That's it. So the entire work actually is being done where? Which part of the algorithm is doing all the work? Partition. Partition is doing all the work. So, if you think about it, what is the cost of partition again? Theta n. So whatever is the size of R minus P plus 1, that's how much work is being done by partition. Because that's n. Of course, when I go to recursive level 1, here and here, then the work is going to be less, but it's still going to be n relative to q minus 1 minus p plus 1, and r minus q plus 1. That's also going to be, those are going to be the pieces. If it's right in the middle, this is really going to be n over 2 and n over 2. But it could be unevenly split. And actually, in reality, it will be unevenly split. It would be a miracle if it was evenly split. How come, what kind of a miracle? Well, if you have 1 million elements, it would take 1 in a million to get that split. And then you'd have to have two probabilities of 1 in half a million. And then 4 probabilities of 1 in quarter million. Okay, you figure it out. It's not very likely that you're going to get perfect splits. And yet, that's what we're after, and we're banking on that. We're hoping for that's going to be true. Okay. So, let's look at the worst case analysis of quicksort. The worst case analysis occurs actually when the pivot goes from here to here. Or from here to here. And why is that the worst case? It's the worst case because the left recursion, if the pivot goes from starting position to the same position, then the left recursion has how much to do? 0. But the right recursion has n minus 1 to do. Of course, if the pivot goes here, the right side has nothing to do, and the left side has n minus 1. Now, why is that the worst? Well, it's the worst because we're cutting the problem in nothing. We're just subtracting 1 from the problem. If we found the pivot in the middle, we'd have 2 halves to solve. And the number of levels would only be log base 2 of n before we got unity at the leaf level. But if we only count 1, and we started with n minus 1 is theta n. And if we do it again, it's theta n. And if we do it again, it's theta n. It's always going to be theta n. And how many times is it going to happen? N times. So that is going to lead us to a complexity of n squared. That's where we're going to get to here. So you see what's going to happen here. We have t of n in the worst case is 0 on either the left or the right, and n minus 1 on the other part. What is theta n? What does theta n represent? PAR? The partition cost. Yeah, that's the actual cost. The only work being done in Quicksort, the only real work is the partition cost. So theta n is the partitioning cost. Now t of 0 you can say is theta 1, but theta 1 gets absorbed into theta n. So now we have theta n minus 1 plus theta n. This is an arithmetic series, which becomes n squared. It's easy to see how that works, because basically what you have is t of, imagine a tree. Imagine a tree. N, this tree is 0, this is n minus 1. This tree is 0, this tree is n minus 1. This tree is 0, this tree is n minus 1, or n minus 2, n minus 3. So we are adding n minus 1, n minus 2, n minus 3 down to 1, or summing 1 through n. Well, summation of 1 through n is n times n plus 1 over 2. Why not? That's an arithmetic series. So that's the worst case. This is our favorite recursion tree. Okay? We can make it any kind of tree we like. It could be a pine tree. All right, so we start off. So what's C of n? C of n is just a constant. So all we're saying here is that, yeah, if you're, now C of n could be replaced by what Greek letter? Theta n. Theta n, yeah. So Cn just means it might not be n, it might be 2n, it may be 1.5n. So theta n would replace all that. Okay, so basically, the worst case scenario is left branch, right branch, actual cost. So we start off with Cn on the top, right? Level 0. This is going to turn into this big fat 0. This is going to be turning into, so n minus 1 goes into here, produces a t of 0 on the left, a t of n minus 2 on the right, and the actual work becomes C times n minus 1. There's actual work. This branch dies. This branch is going to die. And it's going to happen again. So again, it's going to have a t0 here, and t n minus 1. n minus 1 goes in here. T of n minus 2 plus cn. So that's going to, and eventually it's going to go to unity. But the height of this tree is going to be what? How long does it take to get down to unity if you start by decreasing by 1? It's going to take n. So the height of this tree is going to be n. So it's the summation of all the n's from 1, 2, 3, 4, 5, n minus 1, n minus 2, n times n plus 1 over 2, which is theta n squared. So that's the worst case analysis of Quicksort. So the worst case analysis of Quicksort really rivaling, bubble sort, for example. Rivaling bubble sorts, pretty much. Not too far away from that. Let's look at the best case analysis. This is our impossible scenario, right? Impossible scenario says, if we're lucky, partition splits the array perfectly, evenly, so that means what we're going to have is we're going to have the partition cost, but then we'll have 2 times Quicksort of each half. But that's by master theorem n log n, right? Case 2, this is n log n case. Does that make sense? Because our actual cost is n, and n to the log b of a is n to the log base 2 of 2. Log base 2 of 2 is 1, so it's n versus n. That's n. So therefore, master theorem says it's going to be n times Lg of n. Remember that? Now the question question becomes, so that's unrealistic, it's nice, n log n is good, it's nice, but what happens if we always split the array 1/10, 9/10? So if we have 1,000 elements, it's going to be 100, 900. This 100 is going to be 90, 10. This 10 is going to be 9, 1. Get the idea? Get the idea? Okay, so we're going to always split 10%, 90%. Is that realistic? No. Is that great sounding? Doesn't sound great to me. Right? So T of n is going to be T of 1/10 n plus T of 9/10 n plus theta n. So here's the left branch, here's the right branch, and here's the partition at each level. What is the solution? So let's do it. So it looks like this. So we first do C of n work at the top level, and then we have 1/10 of the problem going to the left, 90% going to the right. And again, it's going to be what? C of 1/10 n and C of 9/10 n, etc., etc., etc. So you can see kind of what's going on. So you can see here, so you have 1/10 of 1/10 is 100. 1/10, 100th of 1/10 is also 100. Here we have 9/10, 9/10. Sorry, this is 9/10, and 1/10 of that is going to be 900ths, and 9/10, 9/10 is 8100ths. So it's going to split it up like that. So when we do that, actually it turns out that we have a situation where we actually having a height which is log 10 9th n, where 10 ninths is the ratio of 9 over 10 reciprocal. So it's a log. Well, if this is a log, and each level is doing theta n work, then the height of the tree is log, some log n, then we're going to have a theta of n log n. So theta, so this is going to be equal to theta n log n. So that's really surprising. Now, it doesn't mean that it's going to be better or as good as if we split exactly in the middle, but it says it's proportionally to the best, which is a little surprising. What if we are lucky and unlucky? So lucky means that we have, so this is, if you're lucky, you have exactly 2 cuts in half, the pivot is right in the middle, plus partitioning. If you're unlucky, that means you're going to have exactly 1 cost of L of n minus 1. We don't even show the L of 0 because we know it's going to be 0 because that's the only thing that's remaining. So a lucky produces an even split and calls the 2 unluckies in a partition. An unlucky receives a L of n minus 1 and a call to lucky. Okay, so if we do that, then we have L of n is equal to 2 times lucky plus theta of n over 2 plus theta n. And if we finish this recurrence, we're lucky again. So it's showing us that basically we are surprised that this is as good as it looks. So, what I'm going to do is, I have only a little bit of time, I might keep you like 3 minutes left extra. I'm going to start this analysis. I'm not sure how much time I'm going to have, but I want to show you this very, very nice analysis that I have here for trying to do the analysis of quicksort in the average case. So the average case really is going to say that you have n elements, and the partition can go into position 1, position 2, position 3, position 4, position n, with equal probability. And then, that's our assumption. So the question is, if the probability of the pivot going anywhere with equal probability, what will be the complexity of quicksort? So the most important thing here is to understand how this is set up. So the average number of comparisons. So basically, we're going to recognize the fact that the cost of quicksort is the cost of the count of comparisons. The count of comparisons is the cost of quicksort, because the recursive cost is nothing. The recursive cost simply sets up the new actual cost for different levels. So the cost of all of quicksort is simply the summation of all of the comparisons at all the levels. So we'll set Cn equal to the number of comparisons on average for a quicksort with n elements. And the theorem that we're going to prove is that this is going to come out to approximately 2 times n log n. Let's see what that means. If n is 1,000,000 elements, then n log n is roughly going to be 1,000,000 times 20. Actually, ln of 1,000,000 is less than 20, but we'll just use log base 2 of 1,000,000, which is very, very nice. Log base 2 of 1,000,000 is going to be 20. Log base 10 of 1,000,000 is 6. So that this log will vary a little bit depending on the base, but we're going to have 1,000,000 times this, so between 20 million and 6 million. That's the best possible case. Best possible case. And what we're saying here is that the theorem says that the average behavior will be approximately twice the best case. Now, is that good or bad? Twice, twice, twice. Well, it's actually very good because twice is proportional to the best case, which means that it's theta, the best case, on average. So for example, if n log n for 1,000,000 elements is 20 million, then this is 40 million. Well, what's quicksort? What's bubble sort and insertion sort? Those sorts would be 1,000,000 times 1,000,000, which is 1,000,000,000. That's bad. So 1,000,000,000 is bad. 20 million, 40 million, that's very fast. That's very, very proportional, very nice. Okay, so we'll assume that the average number of comparisons for level 0, but for 0 elements, is the same as for 1 element equal to 0. If you want me to quicksort 0 elements, I'm done with no comparisons. If you want me to quicksort 1 element, then I'm done with no comparisons. So let's see what we got going on here. So this is the most important mathematical setup for this analysis. So remember what Cn? Cn is the number of average comparisons of quicksort with n elements. Okay. So what we have is, I want you to focus from here, from this parenthesis, to this parenthesis, and see what we have here. So basically, so Cn, again, is the average number of comparisons of quicksort with n elements. We're saying this is going to equal to the average number of comparisons with 0 elements plus the average of n minus 1 elements. So we're going to add those together. And then we're going to add to it the average with 1 element plus the average of n minus 2, plus we're going to add to it the average of 2 and with n minus 3, and so on and so forth. Eventually we're going to go to n minus 1 comparisons on the left and 0 on the right. Well, what exactly is this business doing in here? What are all these? Well, all of these, anybody know what these are? How do we get up with C0 and Cn minus 1? And then C1, Cn minus 2? How do we have these? What does it mean that the average cost of comparisons with n elements is equal to 0 on the left, n minus 1 on the right, plus 1 on the left, 2 on the right, plus 2 on the left, n minus 3 on the right?